Hello, welcome back. Okay, so today we will first talk about, we'll enter this new topic called dynamic programming. And then we will spend like 10 to 15 minutes on the solutions to the first midterm exam. Okay. Okay, so this dynamic programming is a type of algorithms that looks like pretty similar to the divide and conquer approach. Okay, but these two types are essentially different because we will see that the divide and conquer algorithms, they solve the sub-problems that do not have overlap among each other. But in the case of dynamic programming, it is, I would say, smarter algorithm that deals with the cases where sub-problems overlap with each other. So we need to avoid solving the same problem over and over again. Okay, and it also this type of algorithm has a pretty broad range of applications. So compared to divide and conquer, I would say that divide and conquer algorithms is is a bit more common, but this dynamic programming is more important in a way that, in a sense that if the sub problems needs to be defined or organized in a way to avoid too much additional computing time or too much extra computing time, then in that sense, dynamic programming is a more advanced algorithm than divide and conquer. Okay, so it's the similar, what I said, the similar place that it's compared to the divide and conquer is that they solve the problems by combining the solutions to the sub problems. Okay, and here the term programming does not refer to the action of typing your programs. It actually refers to a tabular method, or a method that uses a lookup table. Okay. So compared with divide and conquer, we know that the divide and conquer splits the problem into sub-problems, and these sub-problems are disjoint. Okay, and the divide and conquer approach or divide and conquer algorithm can solve the sub-problems recursively and then combine the solutions to all the sub-problems. But dynamic programming applies when the sub-problems, they have overlap. Okay, so some sub-problems share, so there are a lot of repeat sub-problems. In those cases, solving the sub-problems using a recursive style would cost you redundant time, or there will be redundancy in solving the sub-problems repeatedly. Okay, so from the perspective of efficiency, of course, we want to avoid this repeatedly solving same problems. Once a sub-problem is solved, we just want to mark that it is solved, and we don't want to solve it again. So that is the right way. But divide and conquer doesn't, and divide and conquer and the recursive approach does not recognize the necessity that we want to avoid redundancy. Okay, so if the sub-problems overlap, then a divide and conquer algorithm does not more work than necessary. Okay, because repeatedly solve the subproblems without checking whether the same problem has been solved, okay? And the DP algorithm solves each subproblem just once. And after it is solved, then it will save the answer or save the solution to that specific subproblem in a table. Okay, so the next time the algorithm encounters the same problem, it will just look up the solution to the table, okay, to check if the same subproblem already exists in the table. So that's why we call it a tabular method. Okay, so the table is used to save the solutions to all the subproblems. Okay, so these are the, I would say, a little bit abstract, higher level introduction to the algorithm. So we will start from a more concrete example, Fibonacci numbers. So the series of Fibonacci numbers follows the rules that the third number is the sum of the two numbers before it. Okay, so notice that in this series, this one is a result of 0 plus 1. Okay, so only the first two numbers are predefined. So we arbitrarily let the first number to be 0 and the second number to be 1. And starting from the third number, we can define it by summing the two numbers before it. So the fourth will be 1 plus 1 will be 2, right? And the fifth will be 1 plus 2 equals 3. So that's the Fibonacci number. Okay, so the question is, how do we know what the 10th Fibonacci number is? Okay, how do we know, or more generally, how do we know the nth Fibonacci number? Okay, so we already have 7 numbers written down, so it would be easy to just continue from the 7th number. Then we can write the 8th number, which is 5 plus 8, right, which is 13. That is the 7th. And the 8th is 8 plus 13, right, which is 21. And we can easily get the 10th Fibonacci number by writing it on the paper, right? Well, what about the more general question? How do we write an algorithm that computes the nth Fibonacci number? Okay, so because the nature of the question, we can think of the solution to be a function. Okay, we can think of the solution to be a function that takes the integer number n as input and then return the value of the nth Fibonacci number. Okay, so if that is the case, then we can probably think of a recursive algorithm. And because the definition of the Fibonacci number is, in a sense, a recursive, right? We call that the definition is the number is the sum of the two numbers before it. So the nth Fibonacci number is the summation of the n minus 1's Fibonacci number plus the n minus 2's Fibonacci number. So that is a pretty recursive way of thinking, right? So if we think of it as a recursive problem or a problem that can be solved recursively, then it's easy to come up with the implementation, right? We just use this relationship. The nth Fibonacci number is the 2 Fibonacci number ahead of it or before it, right? So we can write a function like this, right? So I leave these blanks so that you will have some space to think up to think of your own solution, and you can think of it as a little practice, okay? But you don't need to come up with a solution right now. So, for example, because this is a set of if-else condition statements, so we basically need to check the inputs. If the input is a negative number, then it's not a valid input, right? So if it's the 0, which means we want to know the first recursive, the first Fibonacci number. So by definition, we know that the first number is 0, right? And if it's the second, then we return 1, right? Okay, so all the other cases can be done by a recursive call to the function itself, right? So we can put the same function's name here, right? But on a smaller case, which is n-1, right? And plus the Fibonacci, the same function on the, I'm not going to write it, but on the n-2 input, okay? So this is a quite straightforward implementation, thinking from a recursive perspective. But the question is this an efficient algorithm? From our experience, of divide and conquer approaches, if an algorithm is a recursive one, then we will need to use the recurrence or the recurrence equation to describe the running time of it, okay? So in this case, we can do the same thing to analyze the efficiency, the running time of this Fibonacci algorithm, okay? So for example, we can start from drawing a recursion tree, actually, like taking some concrete examples to see how many recursive calls will be needed in order to solve the original problem, okay? Say we want to solve the 10th Fibonacci number, okay? So it will be the fib of 9 plus fib of 8, okay? But when we call the Fibonacci the fib function of 9, it will incur another 2 recursive calls, which is fib of 8 and the fib of 7, right? And the fib of 8 will further incur the fib of 7 and fib of 6, and 7 will cause 6 and 5, and so on, until we hit the boundaries of the recursion, like the n equals 1 or n equals 0, okay? But we are not, this is not the only branches, this is not the only branch, the recursive branch that we get, okay? Because all the other calls, like the fib of 8, will also incur further recursive calls, including the fib of 7 and 6. And the fib of 7 here will incur other more recursive calls, okay? And I only showed 2 branches here, and not to mention all the nodes here. In order to solve these problems, the recursive functions will have to incur more recursive calls, okay? So did you see the problem now? There are a lot of repeated computation, right? Because when we solve the fib of 9, we need to solve fib of 8, okay? But after this step is done, we're going to solve fib of 8 again. And in the process of solving fib of 8, we need to solve fib of 7, but fib of 7 is solved again here and here, right? So there's too much computation are wasted solving the same problem repeatedly, which are totally unnecessary. So that's why if we implement Fibonacci problem using this recursive style, it is not the ideal solution. Okay, so it is actually a very inefficient implementation, very insufficient solution. So what about a smarter way? Okay, so actually the typical way that we human beings think of this problem is pretty smart. Okay, so like when we want to know the say the third Fibonacci number, we will first write down the first two, 0 and 1, right? And we simply take the first two, make the summation, and say, hey, I've got the solution to the third number, right? And what if we want to know the fourth, right? We will then simply take the second and the third and sum up the two numbers and directly get the fourth number, right? So if we like it, if we would like to do it on the paper, we will write a array or write a sequence of numbers, right? So after we have solved, say here, we solved the first Fibonacci problem, right? By letting the first number to be 0. And the second, we also solve it here. And we know the solution is 1, okay? But later on, when we try to solve the third one, we will not actually solve them again, but we will simply take the results that are already solved, 0 and 1, right? We'll take the result to tell us that the result to the third one is 1. And when we want to solve the fib of 3, which is the fourth Fibonacci number, okay? We need to, so in theory, we need to solve fib 1 and fib 2, right? But now we already know the solution to fib 2 is 1, and the solution to fib 1 is 1. So we will directly copy these two numbers. We copy 1 and 1 and make a simple calculation of 1 plus 1, which equals 2, okay? And this applies further on and on, no matter which number we are trying to solve. Like the fifth number, we will take fib of 2 and fib of 3, which are already here, right? Which are already here. 1 and 2, we'll simply take them without solving, without using a recursive way to solve them, but we directly take the solutions and we will quickly get a 3. Okay, so I mentioned that we are going to solve it on the paper, right? And this statement implicitly requires or implies that we need some place to store the old solutions. We need to store the solutions or to the sub-problems, to the smaller problems that we have solved before, so that when we need to solve a bigger problems, or when we need to solve the original problems, we can look up the solutions that we already have on that paper, okay? So this paper is kind of serves as a memory space that we need to save the solutions. Okay. So based on these thoughts, we can implement a very efficient algorithm for solving the Fibonacci solutions in a fast way. Okay. So we call it a Fib Fast. It also takes the inputs integer number n, okay? So first of all, it will allocate some array called Fib array to be an array that contains all zeros, and it is in the length of n plus 1. So these array will be used to store the solutions to all the numbers, okay? And we let the elements in the array in the index 1 to be 1, okay? So As long as the input n is 0 or 1, then it just returns what's in that array, okay? Because it's already known. And in other cases, we do not do the recursive call because the function is called Fast, but this function is never recursively called within the body itself. But it's a for loop, okay? It's a for loop that starts from the third Fibonacci number with index 2 to the last nth Fibonacci number, which is of our interest, okay? So what it does is to solve the solution, solve the problem of size I by looking up the solutions to the smaller problem, which is I minus 2 and I minus 1, and then store the results in the i's position of the array, okay? So the sequence is very important. It must start from the third Fibonacci number, because we need to solve all the Fibonacci numbers sequentially, right? In order to know the third, we need to know the first and second. In order to know the fourth, we need to know the second and the third. So that's why we need to start from the smallest problem, okay? So after that is solved, then we can simply return the nth elements in the array, okay? So this fast implementation or better implementation of Fibonacci number apparently would prefer it because it doesn't include the recursive calls, and it's just a one for loop. So it has a linear running time, okay? So it is just a mimic of the way that we are doing the Fibonacci problem on a paper. We will start from the first and then the second and the third until the nth number that we want to know, okay? So we can also know about something, or I would say some little secrets about human mind or mathematical thinking, the mathematical nature of human mind. And we can probably claim that the human intelligence is kind of a dynamic programming style, because we tend to memorize the solutions to existing problems or to smaller problems in order to help us on bigger ones or more difficult ones, which is good because we don't need to, and actually, honestly, human intelligence, human mind doesn't have the capacity to think recursively. The recursive algorithm, recursive thinking is, I would say it's not the instinction, or it's a bit anti-human because we don't have the innate ability or capability of doing recursive calls to solve problems. Okay. So that is about the example of the Fibonacci numbers. Okay, and I would say the Fibonacci number problem is a simple example that showcases showcases how a introductory level problem or introductory example that the problem can be solved by dynamic programming. And as we will see that later on, the two examples, the rod cutting and the matrix chain multiplication problem, are more difficult to directly derive a DP solution. So I have a question: how are we able to return on line 4? Couldn't be out of range. So specialty of the algorithm here is that the index starts from 0. So say the n can be 0, right? But the n cannot be a negative number. If an n is 0, then the Fibonacci array will be an array that contains one element. And we will say the index will start from 0. So this is different from our convention of the pseudocode, which is special because we let the first Fibonacci number to have the index 0. We call it a 0th Fibonacci number to be 0. Okay, and the Fibonacci number with index 1 is actually the second Fibonacci number. Okay, so when n is 0, it is actually okay because the first statement allocates an array that is of length n plus 1. Okay, so if n is 0, if n equals 0, then there will be an array of 1 element allocated. Okay, and we can access that number by accessing fib array square brackets 0. Okay, so that's the specialty about this problem, and it's different from our convention, but actually we can using 1 as a starting index, okay, but which simply needs to change everything in the code. Okay. All right, so now let's look at this a bit more complex problems, but it is also more interesting as we will see the power of dynamic programming in avoiding solving the same subproblems repeatedly, okay, in a more realistic and practical scenarios. Okay. So it's called a rod cutting problem, and it's a very classical example. So the background is like, imagine a company wants to sell long steel rods, okay, and they want to cut them into shorter rods and then sell the shorter rods with different prices. Okay, so we simplify the condition that the length of the rods need to be discrete number, need to be integer numbers. We don't use float numbers, okay? And we assume that the different lengths have different prices, okay? And the cut is free, okay? We don't count the cost of each cut operation. That will make things more complicated, okay? So the goal is simple, is to maximize the revenue, okay? We want to find the best way to cut so that the total profits, the total money we make by selling all these shorter segments or shorter cuts will be maximized. Okay, so we will be given a table. So that table is the piece of information that we know. Okay, and in this table, the first row is the length. Okay, from 1 inch to 10 inch, we have 10 integer numbers. That's the first row, and the second row is the price for each small segment. So the rod of length 1 inch sells for $1, and the rod of length 9 inch sells for $24. Okay, so this is not necessarily a linear relationship. It's not necessarily proportional. The price is not linearly proportional to the price, but we know that the different lengths have different prices. That's for sure. So we'll just use this table as some external information, okay, as some constants that we know about. Okay, so the problem is straightforward. So given a rod of length n inches, and given this table that tell us the prices for each segment. Okay, so the PI indicates the price for a rod of length I inch. Okay, so we want to determine the maximum revenue, Rn, and we want to know how we should cut up the rod and sell the prices. Okay, so this maximum revenue is something we want to know. Okay, and of course, the solution and how we choose the place to cut is also part of the solution. Okay, but we will start from this maximum revenue as the target solution we want to know about. Okay. All right. So we'll start from a simple example. Let's say we've given a rod of length equals 4. Then we will use this table as the input. Because the length is 4 and it's relatively easy to enumerate all possible ways of cutting the rods. Right? There's only that many places because the shortest is 1 inch. Right? So first way or first solution is no cuts. We don't cut it. Then the resulting length is a 4-inch rod, and the price is $9 according to the table, right? Second, we can cut it into 1 plus 3, and the price would be $1 plus $8, which is also 9. Okay, and the third way is to cut it into 2-inch plus 2-inch. And the price is $5 plus $5, which is $10. Okay. Or we can cut it into a 1 plus 1 plus 1 plus 1, which gives us $4. Okay. So we will think of each unique position on that rod as a unique. Okay, so we'll think of the 1 plus 3 different from 3 plus 1. So just for simplicity, so we don't consider the conditions where the 1 and 3 can be switched in order to represent one solution. Okay, so if we consider this rod of length 4, there are 8 possible ways of cutting a rod. Okay, because there are 3 places that we can put our cut onto, right? Indicated by these 3 red lines. So on each red line, we can choose to cut or not. So each red place, each red line, red mark, we have 2 options. Okay, and we have 3 of such places. So in total, we have 8 ways of cuts or not. Okay, but the results can overlap, right? The results some subproblems can be the same subproblems. Okay, so the total number is 8, and in this case, it's relatively easy to go through all the subproblems, right? We just list all the 8 ways to cut, and then say simply list the best solution, optimal solution. Okay, so for a length input of length n, which is more general, then we can do the analogy. There is n to the power of n minus 1 different ways of cutting a rod. Okay, because we have that n minus 1 places that we can choose to cut or not. Okay, so we can use an addition expression to indicate the cutting results. Okay, so for example, the input length of 7, given a rod of length 7, we can use 2 plus 2 plus 3 to indicate one of the solutions, and its other solutions can be like 1 plus 6, right, or 3 plus 3, right, or 1 plus 1 plus 5, and so on. Okay, so that is the notation that we need to know. Okay, so next it's gonna be some important notations we will use. So if an optimal solution cuts the rod into k pieces, okay, and this k must be between 1 and n, okay, and an optimal decomposition of the rod into that many lengths, okay, say we have k of such integer numbers from I1 to I2 to Ik, okay, we have this way of decomposition, right? Just like the way we did for the sevens. So in the case of sevens, then I1 equals 2, and I2 equals 2, and I3 equals 3, right? So that's the case for the simple example. So in the general case where k is less than 9, less than n and greater than 1, then we can use I1, I2, Ik to indicate the solution to the optimal solution. Okay, the optimal solution. So we can represent the revenue, right, by using this P notation, because P is the table that contains the price for each possible length. So the revenue would be the price for selling I1 and the price for selling I2 plus the price of selling Ik. Okay, so these are the notations we will need to use to further formalize the problem. Okay. All right. So now let's use these notations to determine the optimal revenue. Let's see what kind of problems we are actually facing. Okay. So, for example, we want to determine Ri from 1 to 10 using this table, right? So if there's just 1 inch, then we don't have a solution. We don't have a choice. We can only choose not to cut. Okay, and for the input length of 2 inches, right? For 2 inches, we have 2 solutions, either 1 plus 1 or no cut. But of course, the no cut returns better price. It's $5. So we will say that R2 is 5, because for the case of input length equals 2 inches, then the optimal solution R2 is $5. It's also no cut. All right. And for R3, and it's a bit more solutions then, but we can list all possible ways, like 2 plus 1, 1 plus 2, 1 plus 1 plus 1, and no cuts. And we find that no cut is still the best option. Okay. And for R4, which we have seen like 2 slides ago, the solution is 2 plus 2, okay? And we notice that the solution for R4 is 2 plus 2, which is also can be expressed by the solution of R2, right? This time we saw a bit of the flavor of the sub-problems, right? The problem of R4 can be expressed by the solution to the sub-problem R2, okay? That is something we should pay some attention to here. Okay, next, for R5, we still find that R5 can be, the solution to R5 is 13, which can be the decomposition of R2 and R3, right? Because we have solved R3 here. We know that the R3 is 8, and R2 is also known, which is 5. And we have found that R5 is the combination of R2 and R3. Okay. Although here we don't know how we get to that point, but we just show that the solution of a bigger problem is actually comprises of the optimal solution to some sub-problems, smaller problems. Okay. And that is not necessarily the case because, for example, in R6, we found that the R6 doesn't need to be decomposed at all. Right, because the R6 itself is an optimal solution. No cut is a solution, okay? And we can do further splits for larger problems, right? I'm not going to enumerate all the solutions here. So this is just to give you a sense that, okay, the smaller problems solved at the beginning can actually be the resource to, or be the references that we need to use when we solve bigger problems later on. Okay, and the thing, or the technical part is that we want to find how we can come up with the solution. Okay, so let's try to represent a problem with some formal definitions. Okay, so we use Rn to indicate the optimal solution or the optimal revenue for a rod of length n inches. Okay, then we can express it in terms of the optimal revenues from shorter rods. Now we are used a kind of a recursive thinking, okay? So the optimal revenue for n can be defined by the optimal revenues from shorter rods, okay? And we need to choose among the maximum, to choose the maximum elements from a bunch of possible combinations, okay? So here, Rn is the maximum among Pn and R1 plus R minus 1, Rn minus 1, and R2 plus Rn minus 2, blah, 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 until Rn minus 1 plus R1. So these includes all possible ways of doing the first cut after we do the first cut upon a rod of length n. So the Pn corresponds to the choice of not making any cut at all, right? That's directly solved, that is to directly sell the rod of length n. And the second operation here, the second option here, R1 plus Rn minus 1, actually refers to the solution that first makes an initial cut to the rod so that it becomes a length 1 and n minus 1. And then we optimally cut the two pieces further. Because the R1 indicates the best option. R1 indicates the optimal solution to cut the length to cut the rod of length 1. And Rn minus 1 refers to the optimal solution of cut the rod of length n minus 1. Okay, that is something we defined. Okay, user recursive thinking. That's when we talk about the solutions to the rod of length n, we need the solutions to the smaller subproblems. Okay, and similarly to the rest of the items in this maximum choice expression here. Okay, so we need to iterate over I from 1 to n minus 1, and we make an initial cut to make the rod into length I and n minus I, and then optimally cut the two pieces further, and then obtain the revenues Ri and Rn minus I. Okay, and we need to select the best options out of these possible combinations. Okay, but we do not know ahead of time which value I we should choose. We don't know which I to choose. So we have to consider all possible values from I equals 1 to I equals n minus 1, and pick the one that maximizes the revenue. Okay, so if we try to solve this problem, okay, we already have the recursive formalization, right? And then we basically need to kind of implement it, right? So we need to solve in order to solve the original problem of size n, we basically solve smaller problems of the same type. Okay. After the initial cuts, we consider two pieces of independent instances of rod cutting problems. Right. This is kind of similar to the divide and conquer approaches. So the divide and conquer is that after we divide the original problem into subproblems, the subproblem should be a smaller instance of the original problem. And this rod cutting problem is the same case. The resulting problem of solving R1 or R minus 1, Rn minus 1 are the same as solving, they're the same type of problem of solving the original problem. Okay. So the overall optimal solution includes or incorporates optimal solutions to the two subproblems, optimizing the revenues from each of those two pieces. Okay, so we call this optimal structure. And this optimal structure is a term showing that the optimal solution to a problem incorporates optimal solutions to the related subproblems, which we may solve independently. Okay, so this is something we didn't talk about in divide and conquer, but it's basically it describes the properties of the problem that can be solved by divide and conquer. Okay, so it's a more of an abstract description. So we're gonna quickly look at it, and we just have the idea that we can solve the original problem by solving the subproblems. Okay, so let's say before we carry out this implementation, we can do a furthermore slight simplification. Okay, so we can actually place the constraint, okay, by saying that after we cut the rod into length I at the left-hand side and the right-hand side remainder to be n minus I, that's for sure, right? And only the remainder, but not the first piece, can be further divided. That's the constraint we place, okay? So the problem becomes, we need to choose from the max, we choose the maximum elements from these many options. The first price of the length I, which we don't cut anymore, and the remainder part, which is of length n minus I, okay, which we can or we may be place further cuts, okay? So it's a first piece of sub-rod, followed by some decomposition of the remainder. And we will show that this actually includes the cases where we optimally cut both parts, okay? So it includes all possible cases of the previous formulation, which is this one, okay, which we have shown in the previous slide. So this actually makes things easier for us. Okay, so when I equals n, this thing becomes Pn, and the remaining part is R0, which includes this term, Pn, right? All right. So let's see how we can implement this algorithm. So now with the current formulation, like Rn expressed by this formula, the optimal solution actually embodies the solution to only one subproblem, the one remainder, rather than two remainder, and it will be easier. It's like making the recurrence equation having one subproblems instead of two subproblems. Okay, so we can directly implement something like a recursive implementation indicated by this cut rod problem, right? It's given the table P here, and the input length, which is an integer number, okay? So if the length is 0, we should return 0 because it's not defined. It is straightforward, right? The rod of length 0 should cost us nothing. And if the, and we'll define some helper quantity, which is initialized to negative infinity, because this quantity is the smallest possible number, okay? So the function will use a for loop to iterate over all possible positions to place a cut, okay? And after it places cuts, it will compute the price by the price of the left half and the optimal price of cutting the remainder, okay? So this is a recursive call to the function on the remainder length, which is n minus 1, okay? And the result will be combined with pi, which is on the left half, right? This is on the right, left, and this is on the right. The two will be combined as a solution, and this solution will be compared with the Q, so that the maximum Q will be found and returned, okay? And of course, in this cut rod, there will be further recursive calls, okay? So this is how the algorithm can be implemented, okay? But unfortunately, this implementation is not a efficient algorithm, okay? So if we implement it with some programming language and run it, we will find that when the input size is moderately large, then the program will take a long time to run, okay? It's just like the Fibonacci problem, the recursive Fibonacci problem implemented. If we just call some moderately large number, it will be very slow to compute, okay? So actually, if we increase n by 1, the running time will approximately double, okay? So we can easily find out why. So I'm going to put this part in detailed explanations to the next lecture, but we can go through it quickly now, because when the input is 4, right, the cut rod on 4 will call cut rod on 3, 2, 1, 0. Okay, and these recursive calls will further cause 2, 1, 0, and 1 and 0 and 1. So just like the Fibonacci problem, the same problems in the same color will be solved by multiple times, which is totally unnecessary, right? After we solve the problem once, we don't need to solve it again, but the recursive algorithms solve the problems again and again, okay? So if we draw a recursive tree of the problem, it will be something like this with a lot of branches, a lot of bushes, which makes the summation of all the nodes a very large number that actually grows exponentially. We will see a recurrence in this form will be an exponential function. And that's why the algorithm, the implementation in this way is not the ideal way of solving the cut rod problem. Okay, so we will need to refer to the dynamic programming approach by storing the results to the subproblems after we solve it the first time, and then later on when we meet the subproblems again, we just need to use the lookup table to retrieve the results, but not solving them. Okay, so I'm gonna end the lecture today, and the next we're gonna talk about the solutions to the midterm exams.